Hi, welcome to day 6 of the neural network course. And in today's course, I would like to walk you through the usage of neural networks in a very visually representable way. If you look at this diagram, we'll easily see that the inputs that we discussed in the previous class, the A and B, are multiplied with C are multiplied, and the output is then added by C in order to get the value D. So this is the output, and this is a very cool way of representing the weights in the neural networks and how much they'll be changing in order to get whatever output, and how's the output changing. So this is actually extracted from Andre's course, and it actually uses an open source package known as micrograph. So we'll be building all these components that are required in order to store the data, and also to basically use these as variables, which are essentially inputs and weights in our neural network. So to get started, I will just walk you through defining class, which is then used to get to this plot. So the class that Andre uses is defined as value, and where we initiate it with self, and then we'll have some data as an input. So let's do self.data is equals to data, and now we gotta define a reaper function, where it basically helps us to print the value in a better fashion, in an understandable manner. I'll walk you through what this is about. Value of data is equals to, let's do self.data, right? And yes, so that's pretty much it. So let me define our input as a value, and when we print A, it basically outputs A as 2. I'm not really sure why I'm seeing duplicate outputs, but just bear with me about this. Like, it should just print one output, but it's just printing two of the same value. I tried to restart the kernel, it didn't help. So if anyone has any thoughts, please put in the comment section. Cool. So what if we don't have a representation function? It basically prints out some garbage value that we cannot make any sense of. So in this way, we can create any number of variables with any value inside it, like -3.0. So if you just print B, you can see that it has some other value inside it. So this is our base. These are the variables that we'll be using, and here there are two aspects: the inputs and the weights. Both of them will be defined as a class value for us to get started with. So along with that, I think the first operation that we'll do with our data is addition. So in order to create this is an inbuilt Python style, inbuilt Python language. This is built in Python language, where we just take the input data, and then we'll just add another variable which is after the addition, which we call it as other. And yeah, I think that should be it. So let's return this out, and we have two variables, A and B. So let's add A and B. So we can see that 2 plus -3 is -1, which is correct. And yes, I think that's about it with addition. And also we can do the same with multiplication, where we can do self and other. is basically a value with self.data plus other.data. No, sorry, self.data into other.data and return the okay. Let me see what the error is. It's a value function. Yes. Oh, it's another underscore. Cool. So if we just do the same, a multiplied by b, it should be -6. Unsupported attribute for value type. Okay. It's a basic operation. So let me see what's going wrong in here. So value and value cannot be multiplied. That if those can be added, then they can also be multiplied. So define multiplication self and other, and that the output of this multiplication should be a value type where we are multiplying the data of the A with respect to the data of B, since both are values. Something might have overridden, so sorry for the confusion. So yeah, we got the expected output 2 into -3. Now, so the basic operation that we do is A into B plus C, and we can achieve that in the with the data that with the class that we have in hand. So we have defined A, we have defined B. In the same way, I'll also define C. C is a value of let's take it as 10, right? So if we just perform this operation, you could see that the value is 4, which is the expected output. So -6 plus 10 is +4. So the output is now a D, which is actually a value type or class value. Now, in order to get to this visualization, we have to add a few more components to it. The things that we added right now are the inputs, that is 2 and -3 and 10. So along with that, we should also add what variable are we talking about. So in order to add that, we just add labels to this. As simple as that, even while initiating itself, we'll create an empty label. And let's add another parameter, self.label to be label. And now we can easily define a.label to be A and b.label to be B, or we can also do this, label is equals to C. Anything should work. So if we look at C.label, we'll get the output C. So in this way, we know which variable we are talking about at each stage. So here in this case, after we do do the mathematical operation, we can just create this as D, right? Cool. So if you just look, if we try to draw this, since we never defined E anywhere, we will have an operation error. Along with that, there are also different characteristics that we would like to save in our data, such as we would like to know what kind of operation is happening. So is it multiplication or is it addition, etc. So in order to do that, we will also define another empty string, and this string, let's do self operation is equals to operation, and yeah, this basically helps to track on what kind of operation we're doing. For example, A into B. Now let's say d is equals to a into b, then d dot operation will be empty because we defined with an empty string. So the way that we can define an give a label to something is by doing the following. So we are initializing, we are recreating values here with data, and with the data, that is the addition, and we essentially don't give any label because we are not sure which variable we'll be saving this output into. So it's better to give label outside of the um, class. Now, but we are pretty sure that every input that comes to addition, basically we just add, and everything that comes into multiplication, we just multiply. So here it basically means that the operation is going to be addition and operation is going to be multiplication. So when we look at d is equals to a into b, d dot op is going to be multiplication that we have set, and if we do addition, then that's going to be addition. So in this way, this can help to print out what kind of operation is happening under the hood. Along with that, there are a couple more aspects that I would like to talk about, which might make better sense going forward in the lecture. One of the important attribute is children. Children basically means we would like to keep track of what our previous values of a and b are. So remember, in neural networks, we start by just multiplying the input with some random numbers that we call weights, and then look at the output, and based on the output, we start tweaking these weights, we start differentiating these weights, right? So when we differentiate, our weight value is going to change by some margin. So what children does is it helps to keep track of what the previous weight value is before the differentiation and what the current weight value is after differentiation. So hence I would like to call this as the previous value, and that basically is a set type. Android use this for efficiency purposes, so I'm just going to follow the same. And since we are defining children after data, we should most probably add everywhere that we are defining value with basically children. So here we're going to get these are the input values that we're going to get. So in children, we'll save the input values as it is, and it's the same for operation multiplication. So if we look at d, which is multiplication operation, and if we look at the previous values of d, we could see that it's -3 and 2, because the inputs that we used are a plus b, and a is 2 and b is -3. So yeah, I think they got interchanged. Let me let's take this out. Yeah. So yes, so that's the way. That's the reason why we have children over here, for us to make sure what our previous values are. Along with children, we need a couple more characteristics, which I will talk about in future video. But basically, we need grad 0.0, which basically says how much of a gradient descent or how much of a change we are doing, and then yeah, I think that, and along with that, we would like to add another terminology known as backward, that basically is none for now. And yeah, I think we pretty much did it. Now let's see. let the d value be a into b plus c, and yeah, so we recreated the same plot. You could see that our input data is 2 and minus 3, and we have their labels, and we're multiplying, and hence this score which I have extracted from Andrew's lecture basically takes care of all the values of d. That is, we just give d as an input, and it breaks down, it goes through every node and edge, basically, and labels. So node is basically every variable, and it just prints out the label for it here, and then it prints the data present in that, and then it prints the gradient value. Right now we have initiated gradient with 0, and in future lectures I will explain what gradient is about. And then we have the multiplication, which is the operation aspect. So if there's any operation value, then just add that as a as a graph. So if we look at this, we could see that a multiplied by b yields to something that is minus 6, but it doesn't have any variable defined. So let's make this even cleaner by making sure that e is equals to a into b and d is equals to e plus c. And let's give this e dot label as e. Right? Now we can see we are able to print the value e. So bear with me. Along with this, this basically says we have two inputs, a into b, and we have multiplied that, and then we have added a value c to the output of a and b, a into b, and that gave us the output d. So while this is a very simple way of representing, in practice we have many more complex operations that goes on between the input and the output. That is, between the input a, b, and between a, b, and d. Along with e and c, there could be many different operations that can happen. So let me walk you through one small example of what other operations do we add, and in the next lecture I will walk you through the gradient descent operation that changes these input values, or that changes these weight values. So this is too simple of a network, so I'm just adding a layer of complexity here by saying that d is equals to e plus c, and then let's add another constant f, which is minus 2.0, and the label of it is going to be f, right? And then this is our final output, that is d into f, where its label is going to be L. So I hope you were able to follow here. We are basically increasing the complexity of our output from, instead of just multiplying inputs with inputs with each other and adding c, we are going to multiply inputs and add c to it, and then multiply that output with f, and then we get our final function output, or final prediction, if we may call it. So this is basically adding one layer of complexity to the whole equation, and I will walk you through in the next lecture on how can we differentiate, or how can we change, or what values can we change here, so that our L, or loss, or prediction is better. So thank you so much for sticking on this video. Um, take care, good night, and see you in the next lecture.